Welcome. Continue on membranes, and now we're going to specifically talk about how sugars cross the membrane. I added this picture here earlier before COVID, and now it gives me the heebie-jeebies with those big mouths open close to each other. So I added the little mask warning down here. Anyhow, let's go on to moving sugar across the membrane. I've put a picture of glucose here for you to see that it's a relatively big molecule. It's going to still be able to get through using a protein, but it's a large molecule. So how are you going to transport this? Remember that when you eat, you're bringing in a glucose into the lumen of your intestine, where it's going to have to cross the cell layer of the intestine and then fall into circulation. It's got a long way to go, and it's going against its concentration gradient because the cells already have glucose in them, and you're putting more glucose in there on top of it. This kind of movement of glucose does not require ATP, and the way it does that, it's driven passively, and it is done by piggybacking with sodium. So let me show you. It's called secondary active transport or co-transport. So we're going to have a carrier protein that's going to carry that glucose molecule, but it's not going to use ATP. Solute A is transported by diffusion. That solute A is going to be sodium. It just diffuses down from where there's more to where there's less. Solute B is going to be moved against its concentration gradient. In this case, solute B is glucose, and it is sneaking in with solute A. Okay, so that's my example, sodium and glucose transporter. It's called SGLT, sodium glucose GLT transporter. So the sodium is going to diffuse passively, and the glucose is going to be actively transported by sneaking in with the sodium and not wasting any energy. Let's look at the model again. So you have, I'm going to use a pen. You have the model here of what that protein would look like. This is the lumen of, let's make it the intestine, okay? Because we're eating a granola bar or eating that burger. And sodium is higher in concentration here in the lumen, and inside the cell, the intracellular fluid, it is lower. So it'll diffuse naturally from where it's high to where it's low. Okay, here it's showing you that sodium is low. And it's the other way around for glucose. Glucose is low here and higher in the cell. Even though you ate that huge burger, you think that's a lot of glucose, but this cell is doing pretty well with glucose. It's got enough. Okay, so what we need to do is attach this sodium there into a region of this protein where the sodium is going to attach. So let's go on and see. Once that happens and the sodium has bound already to that molecule, the glucose has a separate location on that protein where it's going to be able to attach. And once the glucose is able to attach there, then you have that click mechanism of that carrier that's now going to close itself to the lumen end and open itself here into the cell end. I can write that into the cell end. Here we go. Now sodium is released into the inside of that cell, the cytosol, and glucose is going to follow. So that's a brilliant way to bring this large molecule in without using ATP. When it comes to epithelial transport, think of what's happening. You ate that burger, that glucose now is in the lumen. You have to get it into the cells that line the intestine, but that's not enough. You've got to get it from there now out the other end and reach circulation to get that glucose in the blood, so you can distribute it to every cell, not just to the cells that line the intestine. Okay, so these mechanisms of moving things through the cells have specific names, and let me enlarge it for you. If it is going out into the lumen, it's going to be called secretion. If, however, you're taking something that's in the lumen, part of that burger, and bringing it in this direction, then it's going to be called absorption. Okay, secretion out into the lumen, absorption into the cell from the lumen. So back to our transporter. If this is where your burger is, it's coming down the lumen, and this cell is lining your intestine, we're going to bring in the sodium. We're going to bring in the glucose. It's a co-transporter, symport, going in the same direction, and that's excellent. We have it inside the cell. But we don't just want it inside the cell there. We want to bring it out to the other end of the cell here and dump it in the blood, right, into the circulation over here. So that's just the first step of what's happening. So let's see what happens next. This GLUT transporter transfers that glucose to the extracellular fluid by facilitated diffusion. So I'm going to have another protein here that's going to now transport. Normally, it's going to be from high concentration in the cell to a lower concentration in the interstitial fluid. So now it's easy. I'm going from high to low across with a transporter, with a protein. That's fine. I've got my glucose where I wanted it to be, and it can go into circulation. But what happens to the sodium? So now I have all this sodium inside the cell, and really I would rather it not be there. I would rather it be back out where it was before. So what happens is that it pumps the sodium back out of the cell, but the only way it can do that is by bringing in some potassium. So this here is the sodium-potassium pump, and this sodium then is going to be able to be eliminated from the cell from where it was in low concentration to higher concentration. So it's a pump because I'm going against the stream essentially and bringing potassium in. So this pump then will be able to restore that original sodium concentration outside of the cell and not just harbor lots and lots of sodium here inside the cell. We don't want to do that. I hope I'm going to step back. I hope that was clear how it is that we can get glucose transported and then restore the sodium back to its original configuration. Check these diagrams in the text. Another form of transport is the vesicular transport, where you are too big for the membrane, you're too big for the protein, and you have to just essentially barrel on through and disrupt that membrane, and then it'll reassemble again. So I'm saying here, how do you transport molecules that are too large for channels or too large for carriers? The form is through endocytosis or exocytosis. So let's start with endo, inside. Endocytosis cell is the transport of molecules or large particles into a cell using a vesicle. If what's coming inside is something that the cell is eating, like a bacteria, it's going to be called phagos, which is to eat, phagocytosis. If it's a fluid, it's going to be sort of cell drinking, not cell eating, and that's going to be pinocytosis or pinocytosis. So all these are coming into the cell. This is a really good diagram of that. This is my membrane in orange. I have a solid particle that cannot fit through the wall, through the membrane. It can't use a carrier. Instead, it's just going to bump up against it. These sides here are going to close up. And I'm going to be able to bring this particle inside the cell. Notice that a piece of that lipid bilayer is actually going to come with it. So it's bringing a piece of the fence with it. If it's fluid, it's the same. Some fluid is going to accumulate. This is going to pinch off here and end up with a vesicle because it has a piece of the membrane with fluid inside. Examples of endocytosis. Exocytosis is exactly the opposite. You have a vesicle that has a lipid bilayer. It moves towards the edge of the cell. It fuses here with the actual membrane that we started with. And as it fuses, it will open up its contents. Let's make sort of a break here. Open up its contents and release what was inside that vesicle. So these little particles here are these here. And that's exocytosis. There is a running problem on cystic fibrosis of the defective channel, and I want you to be able to look at that and study that because I might put some questions on the cystic fibrosis question. It's a running problem in your book where it gives you a case study. And I want to stop there. Thanks for listening.